welcome to tonight's session on chair conformations. When you get to organic chemistry, you're looking forward to all the chemistry and all the science and all the reactions and all the mechanisms. And instead, you're asked to draw a hexagon. A very pretty and very beautiful, somehow very difficult to draw hexagon, which, quick trick, you just draw two parallel lines, put a dot above and below. Notice how even though it's messy, it looks like a very clear and very obvious hexagon. I highly, highly recommend that you use this method so that you don't lose points for having a drawing that your professor doesn't like. Now, this hexagon representing cyclohexane has a slight problem. And that slight problem is, well, what is it made of? What is the hybridization of every carbon atom in this cyclohexane flat hexagon? We don't have any pi bonds. We don't have any charges. They are all sp3 hybridized. Now, an sp3 hybrid, you hopefully know, is an ideal 109.5 degree bond angle between the carbon atoms. But the way we have it here, and I have a molecule ready to show you so you can see what I mean. I have, well, this thing is almost broken. I had to scramble to find these pieces because my son thinks these are building blocks. He's almost 3 and he thinks this is a toy for toddlers. He wants mommy's model kit. So here I am trying to make a perfect hexagon. And you'll notice that my kit is bending, it wants to break. This is not ideal. Look at these bond angles. They are being stretched to a lot more than 109.5, and that makes it very, very unstable. This is what brings us to everything we're covering tonight. If I want my model kit to not break, I have to push these out a little. Push this one here. I'm alternating one going to the right, one going to the left. And now they're approximately 109.5. And look how much happier this thing looks. It still looks like it's going to crack here because I've demonstrated this too many times. But it looks a lot more stable. If you look at it from the side, you can almost imagine this is where you put, let me see, how are you seeing it? Yeah, this is where you put your head, you lay your body, you put your feet down, maybe a nice margarita or a drink, and you have yourself a chair conformation. Cyclohexane does not want to be a flat hexagon. It wants to be a chair conformation. So what does that look like on paper? What does that look like, well, when you have to do this in class? Also, with regards to the model kit that I just demonstrated, if you go to leiaforsci.com/kit, this is the one I recommend. So I have a video on how to use that as well. And I'll also put the link in the description. When we're drawing the chair conformation, the way that you'll see it in your textbook looks something like this. And even that looks kind of drunk. So the chair is drinking, not just what you're doing on the chair. And the problem is your textbook is using a computer-generated image. But if you're working on this in class, if you're working on this, if you're drawing this on your exam, you want it to be very, very obvious what is going on. And this right here, if you have your ups and downs confused, you're going to lose points. And so instead of the drunk chair, I'm going to show you a different way to draw it that is going to look a little bit different than what you've seen in your textbooks, but guaranteed to gain all your points because everything is very obvious. You draw two parallel lines that are offset from each other, one slightly to the right or slightly to the left. You see this opening right here. Just draw a point at the opening and then connect the dots. Just draw a line to that opening. You can do the same thing on the other side, but I'm just going to draw an imaginary dot in my mind. You see how it looks very different from here, but it's still kind of obvious what is going on, right? That right there. There's my chair, and there's the margarita. So just as acceptable, easier and faster to draw. I could do the same thing in the other direction. So notice my two parallel lines. I had the upper line towards the left. And now I'll do the same thing with the upper line towards the right, like this. I have that imaginary dot, and you can draw it out if you want to, but I'm just drawing as if there's a dot there. And then on the other side, same thing, as if there's a dot there. That is the foundation of my chair conformation. Before I continue, I want to see a couple of hearts in the comments if this already saved you some time and confusion for your upcoming quizzes and exams when it comes to drawing this. And I see the hearts coming in. Excellent. So what happens though if I have substituents? What happens if I need to put something onto this model kit, onto this chair conformation, which I could show you in a model kit after? How do I draw them? So for example, if I have a molecule that looks like this, let's go with a cyclohexane and a tert-butyl group, something big and bulky. Let's make this one coming out of the page on a wedge. Okay, now that looks drunk. Let's try that again. There we go, a tert-butyl group. And then let's put a methyl group going down and into the page. What does that look like if I want to put these substituents onto the cyclohexane? So let's go back to just the model kit. And I don't have a tert-butyl group prepared, but we'll just use this, whatever I happen to grab. And let's also get, let's see, what do I have? We'll take this small one. So this small one here will represent the methyl group. This pink one here will represent the tert-butyl group, or rather just think of it as the big bulky group and the small group are the two that I want to represent. Now, the way I have the hexagon drawn, I have it where towards, actually, I think I might be seeing it backwards to how you're looking at it, but whatever, we'll just go with it. So yeah, I think this is how you're seeing it. So there's a group coming out of the page at you over here. Let's get this connected. And then there's a group going down, but into the page here. Up and out of the page, down and into the page. If I can get the, nope, that's the wrong spot. I have it like 1, 2, 3. No, that was the right spot. Okay. How do we draw these substituents? Let me connect this. Oh my goodness, this is so hard to connect. Okay. I still recommend this model kit, even though it requires a little bit of muscling. How would I show something like this on my drawing? How do I know where the lines go with regards to my substituents? So let me just show you. If I look at it this way, I said that one was going up, one was going down, and then I had it shown to you initially like this, where the big bulky group was coming out of the page with a wedge towards you, and the small group was going away from you into the page. See how it's coming towards me and away from you. So let's play with it on paper for a bit and then go back to that. Just lost my spot on the notes. Okay. If I'm drawing the substituents, let's actually go back to the kit. And this time, let's ignore for a moment what they are. Just take a look. Let me take them off. Look at all the groups that you have coming out of it. Notice that I have some that are going up, but they're going straight up. Some that are going up, but they're kind of sideways. And then going down, I also have some that are straight down. And some that are down, I actually pointed up, down, 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 but kind of sideways. First, we have some questions. Wedge is towards you and dashes away. Yes. So the way I want you to think of it is a wedge is coming towards you and it's getting bigger and bigger and bigger. The dashes are kind of fading away. They're going down into the page. Okay. So again, wedge coming towards you, getting bigger and bigger. Dashes are going away from you into the page. Davin, just want to say I got a 113 on my first. Wow. Okay. Thank you for letting me know. That is very cool. I am honored and congratulations. That is awesome. So let's go back to the substituents here. Notice that the ones that are going up, these are pointing up in the y-axis, and the ones that are going down are pointing down in the y-axis. Up, axes, down, axes. These are called your axial substituents because of the axes. Notice that if it's not pointing straight up, it's kind of pointing out. It's pointing out. So if I were to turn this chair into a circle and then draw a line, or I guess a circumference around it, notice that these are pointing towards that circumference around the chair conformation. If we think of that circumference as an equator, it's pointing towards the equator. Well, let's make this a little straighter. There we go. So all the ones that are pointing out towards the equator, these are called your equatorial substituents. Axial, equatorial. Axial, equatorial. I want you to also notice that the way this is oriented, notice the carbon that is up has an axial up. Down has an axial down. Up has an axial up. And it follows this pattern all the way around, where the equatorial, the equator, is the exact opposite. And the other pattern I want you to see here is that it goes up and down, alternating. Axial up, axial down, axial up, axial down, axial up, and axial down. And the equatorial is going to be the opposite. Equatorial down, up, down, and up. So that is how it looks on the model kit. And that is also how we want to make it look on the drawing itself. So if I go back to this, and let's actually do this with a brand new clean one. When you're drawing your substituents, instead of thinking what is axial up or down, what I recommend is first starting with just the skeleton itself. This is what I call the turning off your brain part, because you don't need to think. You find one point on the molecule and you say, if I'm starting here at random and the up tip of the chair, that carbon is higher up, then I start axial up. And then all I have to do is follow the pattern around. Axial up, down, up, down, up, down. Didn't really require much thinking. It just is a pattern that I followed. Then if this one has an axial up, then the down would be equatorial. And once again, we follow the pattern. If this is equatorial down, then I go up, down, and up. Notice here I drew it to the left. I could have just as well drawn it to the right. Same thing here. It would not have made a difference as long as I chose one. Make sure, though, that you don't draw it down, straight down, because your professor will take off points if it looks like it's ambiguous. If your professor cannot tell axial or equatorial, it doesn't work. Now that we have our skeleton, that was the part where you turned your brain off. Now we turn the brain back on, and let's see our molecule. It doesn't matter which carbon is which, as long as I'm consistent with my substituents being up and down the way I have them here. So what I'm going to do is randomly number this carbon 1, and then I will go clockwise. Why am I going clockwise? Because I felt like it. I could just as easily have gone counterclockwise and it would not have changed anything. It's just about choose a direction and be consistent. So if I chose to go clockwise, I will randomly also call this number 1, but you know what? I could have called this number 1 or this number 1. It doesn't matter as long as I am consistent. And if I went clockwise on one, I go clockwise on the other. And it does not matter which is which as long as they're consistent. And then this model kit that I was showing you is only for demonstration. For teaching purposes, do not use a kit. Watch me do this without a kit. On carbon 1, I have a wedge with a tert-butyl group. That means on carbon 1 in the up position, I put a tert-butyl group, and I already know it's axial because I turned my brain off, drew the skeleton, and now I know exactly where it's going. On carbon 3, I turned my brain off, drew the skeleton, and now I see carbon 3 dashes means down. I'm looking for 3 down, happens to be equatorial, which we kind of saw on the model kit, but I'm showing it to you here. And that's it. That is the correct, or one of the correct drawings for this molecule. And I did not have to use a kit to figure out what was what. So let me go through the steps with you really quick. 1, you're going to draw your chair without looking at your molecule. Just draw a chair. 2, you want to add lines for the substituents. This way you know what is axial or equatorial. 3, you want to number both your flat hexagon and your chair conformation in the same direction, both clockwise or both counterclockwise. And then 4, you simply match up the carbons and add your substituents. And they immediately go where you wanted them to go. This was one option, though. Remember earlier I showed you that I could have drawn the chair in a different way. Notice my parallel lines here have the left side going up and the right side going down. What if instead I wanted the right side going up? Give ourselves a little bit more room. The right side going up and then the left side going down, so it looked something like this. Would that work? Well, let's see. Let's do our substituents. I pick the up tip up, down, up, down, up, down. Then I do the opposite for equatorial, down, up, down, up, down, and up. Number it randomly so that I have clockwise 1, 2, 3. I'm choosing here at random because why not? And then I add my substituents. On carbon 1, I put a tert-butyl. On carbon 3, I put a methyl, and the tert-butyl goes up, the methyl goes down. This is another correct option for this molecule. So let me ask you, is the correct option the one I drew on the top left or the bottom right? Which one is it between these two? And the answer is, this is called a ring flip. So they are both correct, and the molecule can technically interchange between the option I showed you on one side and the option on the other side. So let me show you what that means. If I have my model kit, and then on carbon 1, I have a group going up. Looking at it from the top, it was clockwise like this, 1, 2, 3, going down. The first version I showed you had the tert-butyl group, which we're calling this big, bulky, obviously non-tert-butyl wedge coming at you. The second one had the methyl going down. If I look at it this way, notice it matches up with my first drawing because I have the tert-butyl group going up in an axial position and the methyl group going down in an equatorial position. So again, I have the tert-butyl up in an axial position and the methyl, this gray thing, going down equatorial. But if I take this chair and I flip this carbon down, and then I flip this one up, notice that I still have, hold on, up, 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 down. Something looks a little bit off. Here we go. This one has to go like this. It's easier to do on paper. Up, up, and up. Okay, there we go. Now, notice that the pink one is still in the up direction, meaning it's going in the general up, but it's in the equatorial position. The gray one is going in the general down, but it's in the axial position. Straight down, equatorial up. All I did was flip the ring. So let me show you the ring flip one more time. I take any carbon that is down and move it up, or I take any carbon that is up and I move it down. I'm basically looking to change. You see how these 3 carbons are up and these 3 carbons are down? I'm just looking to reverse that. So if I take this right here, and let me see how to show you this one. Okay, notice the one with the pink one. That's the obvious one to show you. You see how as I'm doing this flip, hold on, let me see how to do this. Okay, I messed it up. That should be up, that should be down, that should be up. Hang on, this thing wants to break. So I'm trying to show you where this one is, like this, like that, like that. Oh, there we go. Okay, so this is what you have. Now, all I do is I flip that one. I'm just alternating them, and the whole thing is trying to turn with me. There we go. And there's my flip. So again, if I flip it like this, there we go. Now, notice that as I'm halfway through this flip, I get this weird shape, which if I turn it over, that kind of looks like a boat. Do you see how that kind of looks like a boat just rocking in the water, rocking in the water? This is called the boat conformation. Some professors will test you on it, so it's worth understanding what it is. It is an unstable intermediate because in order to go from one to the other, you have to flip one side, flip the other side, like that. But they don't happen simultaneously, so the boat is what you're going to see in the middle. And the reason this boat is unstable, let me demonstrate here. You see this group right here, and you see this group right here. They are way too close to each other. These groups are very, very strained. They're in each other's personal space, and that makes the boat conformation very unstable. So if I go back to the chair, now everything is a little bit more out of each other's face, but we still have some interactions going on here. We'll come back to that. So let's first hold on to this ring flip and go back to the paper, the digital paper that I'm drawing on. So this right here is a ring flip. And the way your professors will show you, and type 1 in the comments, and if you're watching the recording, let me know as well. Type 1 in the comments if this is how your professor taught you to do a ring flip. We're going to take this molecule as the first one that we've drawn. And then your professor said, okay, to do a ring flip, you want to look at your molecule. You want to take your top carbon and drag it down, and then take this carbon and drag it up. And then see where all the substituents go and see where all the craziness is happening and basically just draw a mess. Let me know if this is how you learned it. And let me know if you don't like this method and you want an easier and faster method. I'm going to assume you said yes, because I know there's a bit of a delay in the chat. A much, much better way to draw the ring flip is actually what I already showed you, and that's the following. Just look at how you drew your parallel lines and draw the opposite. So if you have, in this case, left over right, what did I tell you to do earlier? All I said was draw your right over your left. Now, here's the best part. No confusion, because we're not going to look at this at all. Not at all whatsoever. Instead, I am going to finish drawing my chair, close it up, draw my substituents, axial, equatorial, up, down, up, down. So I'm just following a pattern of up, down, up, down. And then once I have a new skeleton, now I'm going to draw my substituents. And let's make this a little bit bigger. And how do I know how to do a ring flip? All I do is find one position, and I ask myself what happened. If this group moved up, let's actually find where we have numbers. So 4, 5, and 6, still going clockwise. So if number 6 moved up, which is what your professor taught you, but no visualization, we're simply moving number 6 up and then drawing the same direction. If clockwise, then clockwise. Just copy the numbers exactly. 6, 1, 2, 3, 4, 5. And let me prove that to you. Notice that number 3 moved down and number 3 is right there. It's down. I don't need any other comparison, nothing else. I see that carbon 1 has a tert-butyl group in the up position. I find 1, I put a tert-butyl in the up position. I see that 3 has a methyl in the down position. So I put a methyl on 3 in the down position. And that is a much faster, much easier, in my opinion, much easier ring flip. Let me see a couple of thumbs up in the comments if this just saved you time and confusion on your next exam. And while you're typing those in, let's see. Studying for the ACS. So for the ACS, these shortcuts are even more important because it's multiple choice. You have less than a minute per question. You need to be that sharp. So I challenge you to learn this trick to save time so that you will get it right. Erica said, this is exactly what we're doing in class right now. Erica, I'm guessing you mean the long and tedious ring flip. And if that's the case, I challenge you to not bother with that method. Only use the easier method that I just showed you so that you're going to save a lot of time. All right, so now that we know how to do the ring flip, I want to talk about some simple rules. I showed it to you on the model kit, but I want to make sure that you're with me so that you get these pieces much faster. Notice that when I did the ring flip, the tert-butyl group is up, the tert-butyl group is up, the methyl group is down, and the methyl group is down. So the first rule I want you to remember is that in a ring flip, Some things change, but not everything. Rule number 1, up stays up and down stays down. On your drawing, a dash remains a dash, a wedge remains a wedge. The only thing that changes is that axial is going to go to equatorial, and equatorial is going to go to axial, but they stay in their lane. They stay where they started in the ring, so that up stays up and down stays down. So let me show that to you again on the model kit. Notice the pink group here. If I do a ring flip, this thing is, let's pretend this was good enough. Very smooth, easy, automatic ring flip because the model kit's not behaving. Notice that this is still up equatorial. Let's try that again. Ring flip. Notice that it is up axial, up equatorial, up axial. No matter how I flip the ring, axial or equatorial will change, but up stays up and down stays down. So let's look at this one here. Notice that it's down equatorial. If I do a ring flip, let's pretend that was a perfect ring flip. Down stays down, equatorial, down stays down, axial, down stays down. I'm totally breaking this thing, but hopefully you get the point. Down stays down, equatorial becomes axial, axial becomes equatorial, but never, ever, ever flip the ring like that. That is wrong, and you will lose points on your exam, so I don't want that. Well, your classmates will lose points on your exam, but you will know not to do that. Question: will this be available to watch later? Absolutely. If you go to the link on the screen, layforsight.com/orgolive, you will get access to all my notes and drawings from tonight, my chair conformations practice quiz, and a link to all my live streams that I've done, all my other quizzes, worksheets, and everything else. So go to the link layforsight.com/orgolive. It's also the pinned comment, so you're able to catch up if you missed the beginning. Learned easier method this week. Thank goodness. Excellent. That is good to hear. Awesome. All right, so let's continue. So we now know up stays up, down stays down. We have the ring flip shortcut. Let's try a couple of practice problems, and let's talk about stability. Say you're given a cyclohexane, and you're given an ethyl group, a methyl group, and let's go with a tert-butyl group because that makes the stability very, very obvious. All right. So for this question, you are asked to draw both chair conformations, meaning draw the ring in both ways, and determine which one is more stable. So the first thing we're going to do is not even look at the molecule. It doesn't matter what the molecule looks like. We want to have our rings drawn and ready to receive substituents. This, I'm telling you, it is a faster way. All you have to do is draw two chairs. So this one has the left up. This one has the right up. Then you're going to add in your substituents. Start with an axial. So I have up, down, up, down, up, down. Same thing here, up, down, up, down, up, down. Let's add our equatorial. Again, this is still the turn your brain off portion. Just adding in all my substituents. And now I'm finally ready to look at the molecule. It doesn't matter how I number, and so I'm purposely going to number it reverse of what I did before to show you that it doesn't matter. I will call this 1 and go counterclockwise. I will randomly call this 1 and go counterclockwise. And then, because I did a ring flip, if this got dragged down here, then I will call this 1 and go counterclockwise. Now that I have everything set up, let's see what my substituents are. On carbon 1, I have a wedge with an ethyl group. A wedge means coming at you, up and out of the page. That means on carbon 1 in the up position, I have a CH2CH3. In the up position on carbon 1, I have a CH2CH3. On carbon 5, a wedge coming up at you is a methyl group. Carbon 5 has a CH3 up. Carbon 5 has a CH3 up. And then last but not least, on carbon number, what do I have? Light blue, green, let's go with this color. On carbon number 4, I have a tert-butyl going down, dashes down away from you. That means I have a tert-butyl here, and I have 4 is a tert-butyl here. And here we go. I have my 2 chair conformations. That means there's a ring flip to get from one to the other. But the question now is, which one is more stable? What do you think? The right or the left? And more importantly, why is that more stable? Don't worry, this is tea, not drinking coffee at 9 p.m. Remember when I showed you on the model kit? Let's see. So when I showed you on the model kit that I have this substituent here, hold on, I have to put it this way. Here we go. When it's in the equatorial position, notice that it points out into the equator. It just goes far away. There's nothing else here. It gets a lot of personal space. It does not have any neighbors. It doesn't have anything next to it. The equatorial position is very, very stable. But if I do the ring flip, and now I have this in the axial up position, it's kind of close to this one right here. You see this hydrogen is kind of in its face. Now imagine I had another group there. So a hydrogen is kind of small. But imagine I had another substituent. Do you see how they are very close to each other, getting into each other's personal space? Axial substituents are not very happy. They do not like being next to another axial substituent. These are not stable. With a ring flip, I put them both into the equator, and now they're so much more happy because they're not in each other's personal space. So again, with these 2 bigger substituents, equatorial, this molecule is so much more stable. But with a ring flip, if I put them axial, now in each other's space, very, very unstable, and we want to avoid this as much as possible. The bigger the group, the bigger the issue. Now, this is just some random piece that I grabbed, but if this was a tert-butyl group, it would be a carbon, and then 3 other carbons like a giant umbrella crashing into that other group. Very, very, very unstable. So let's look back at what we have here and see which one is more stable. There's 2 things that I'm looking for. One is how many groups are axial and equatorial, and 2, what is the size of each of the groups. For the first one, I have the ethyl group is axial in the up position. The methyl group is axial in the up position. The tert-butyl is equatorial, also in the up position. The up and down actually doesn't matter. It's the axial and equatorial. And more importantly, if more than one is axial, then they get in each other's faces. On the right, for the ring flip, the ethyl group is equatorial. The methyl group, wait, something's wrong. I put the tert-butyl in the wrong spot. That tert-butyl is supposed to be up. That's right there. Okay, that makes more sense. The green methyl is in the equatorial position, and the tert-butyl is in the axial position. Had I given you anything else, this would have been the less stable molecule because I have 2 axial substituents that have diaxial interactions. That's what this is called. This is a diaxial interaction, and some professors will actually give you the charts for how much energy, how much friction that causes in the molecule, and you'll have to calculate the instability of the molecule. The diaxial interaction is unstable, but in this case, and this is a tricky example, it's balanced out by the fact that the tert-butyl group is in the equatorial position. So this right here is such a large and unstable group, it actually prefers to be equatorial. And this is going to be what makes this molecule more stable, even though you have more groups in the axial position. So a way to think of this is if you ask 3 people where they want to go out to eat, and one says Italian, and one says pizza. You probably want to go where 2 people say they want to go. And in this case, where they want to go is equatorial and equatorial. But the 2 that want to go for Italian aren't that fussy, and this one is going to throw an absolute fit. So that would be, I don't know, some kind of toddler throwing a temper tantrum. I'm just thinking of my kid when he does not get his way. It is a loud and obnoxious and painful and very, very stressful situation. And so in this case, the molecule will give in. These two will put up with a diaxial interaction just so that this large group can be in the equatorial, more stable position. Looking over to the right, equatorial stable, equatorial stable. Now, typically this would make the molecule more stable, but that right there is so unhappy. This is a large group, and it is so unhappy. It does not want to stay in this axial position, and that makes this the less stable molecule. Again, if your professor has you calculate the kilojoules per mole for each interaction, you'll see that this is such a high number, and therefore this is the more stable, more preferred chair conformation. So I threw you into the deep end here with a hard one. Let's take it a step back and try something a little bit less difficult. And let's go with this molecule right here. And we'll have a CH3 going up. We'll have an ethyl group going down. And then we'll have another ethyl group also going down. What is the quickest way to draw both chair conformations and make sure that we can identify the more stable? Well, the quickest way to do that is not look at the molecule at all whatsoever. Let's cover it up. We'll draw two conformations for the chairs. One I have left over right. The other one I'll have right over left. Turn them into chairs. Turn them into chairs. This is again brain turned off. Put your substituents up, down, up, down, up, down. Other substituents down, up, down, up, down, up. Same thing for the other one. Up, down, up, down, up, down. Equatorial, down, up, down, up, down, up. And we're randomly going to number these clockwise. 1, 2, 3, 4, 5, 6. Drag this down. 1, 2, 3, 4, 5, 6. Also clockwise. And that means we have to number this clockwise. So I'm randomly numbering it like this just to show you it does not matter. All right. Let's see how to do it. Carbon 1 has nothing. 2 has nothing. 3 has a methyl in the up position. 3 methyl in the up position. 3 methyl in the up position. 4 has an ethyl in the down position. 4 ethyl down. 4 ethyl down. And then 5 has nothing. 6 also has an ethyl down. So that's an ethyl hiding in there. And 6 has an ethyl hiding in there. I feel like this is not very obvious. So what I'm going to do is, let me show you something that I can do here. If I change the numbers, I can actually number this however I want. And so when I did the ring flip, if I flip this back, flipping it up is what I had here, but I can also flip it by turning it this way. I want to see if this is going to make the substituents more obvious. Same exact thing. I'm just trying to not have them hidden on the inside. And so let's see if I can redraw it. So remember I showed you where I turned the molecule. You can just kind of turn and turn and turn. Same thing happens here. So 3 in the up position is a CH3. 4 in the down position. No, it's still hiding. I should have thought this one through. And then 6 in the down position is also an ethyl. Okay, so only one of them is hiding right now in there. So let's not forget it. But all I did was flip it in the other direction. Same thing. All right, correct downs and ups. Methyl, up, up. Ethyl, blue, down, down. Ethyl, purple, down, down. Excellent. All right, so which one is more stable? Well, let's see. On the left, I have an axial up. I have an axial down and an axial down. On the left, I have an equatorial down, equatorial down, equatorial down. Well, that one's actually very easy. It didn't matter how I drew it because what I have here is 3 axial, which are kind of unhappy. This one's unhappy, but it's only got hydrogen in it. to interact with. These two are both axial down. They're clashing into each other, so that is very unhappy. This one, I have 3 equatorial. This is about as happy as it can get. This is going to be the more stable because I have more substituents equatorial. This one is less stable because I have, well, all the positions are axial. All right, if you are with me so far, if this has been helpful in helping you save a couple of minutes, even if you're watching the recording, I want you to let me know in the comments which shortcut that I showed you is going to be the most time-saving on your upcoming quiz or exam. And then I want to give you a sneak peek. So someone asked earlier if you have to know Newman projections for this. If your professor wants you to know Newman projections, let me just think how to do this. Okay, so sometimes you'll get a question that looks like this, where you have a CH2 right there, a CH2 right there. Let me know if this is starting to look scary. Okay, an OH, an H. Probably should have drawn this out earlier now that I think about it. All right. This right here can be turned into a chair conformation. What you have to do is recognize where that hexagon is hiding to see where your chair is. Don't forget that this right here is a carbon and behind it is another carbon. So that right there, whoops, I don't know what I just did. Okay, that right there, 1, 2, 3, there's a 4th one back there, 5, 5, and 6 right there. These are your 6 carbons that make up your hexagon. Why do I keep pushing all these things? Okay, so if I were to draw this out, the carbons that make up your hexagon look like this. These are the 6 carbons where the CH2, that's this CH2, this CH2 is this CH2. That means I have this carbon here has the OH, and then this carbon here has the Cl, that's this one, has the Cl going down. So the way that you would draw that is the OH is going up here, the Cl is going down. Remember, dash is down, a wedge is up. On the rear carbon, that is the one that's back there, the bromine is going down. And then the rest are just hydrogens. So the only substituents I have on this chair are OH, Cl, and Br. It looks so scary drawn in a Newman, in a double Newman. Now, this obviously looks a complete and total mess, but you can turn this into a chair because now that you have the hexagon, all you have to do is draw your chair conformation. It doesn't matter which one. So I'm just going to start by showing you one. I have my chair. I'll number it clockwise or counterclockwise. So let's randomly draw it like that. And then same thing here. We'll randomly do it like that. And look what I have. Oh, wait, I have to do the turn off brain part just so I know where my substituents go. When you do this, by the way, on your exams, make sure you fill in hydrogens wherever you don't have a substituent so your professor doesn't think you're drawing methyl groups, because a line technically is a methyl group. So you don't want to lose points for that. On 1, I have an OH up. On 5, I have a Cl down. On 4, I have a Br down. And there you go, my double Newman as a chair conformation. And now to turn it back into a Newman, or even more practice. So this is actually a question that came out of my practice quiz. If you go to leahforsyth.com/orgoalive, the link on the screen, you'll get, just sign up on that page and you will get access to what I shared today. So anything that I drew here, a copy of these notes, as well as the chair's practice quiz with this question. This is one of the bonus questions. So you'll have a lot more of the standard practice questions that you're used to seeing as kind of warm-ups. So the basics and stability and drawing chairs and ring flips and all of that. The link again, leahforsyth.com/orgoalive. If you're looking for even more, including the step-by-step, less rushed version, because I know I went through this a little bit fast, of how to solve all of these questions, how to do each of these in a lot more, not just a lot more detail, but the step-by-step of this is how to approach it, this is the logic behind it, this is how it means, this is how it's done. I cover all that in my Organic Chemistry Study Hall membership, which you can sign up when you go to leiaforsci.com/join. As a Study Hall member, you'll get access to my entire Organic Chemistry 1 and Organic Chemistry 2 video library so that you can have all the topics broken down from simple to advanced with tons of practice and step-by-step explanations every step of the way. And most importantly, if you get stuck, if you have questions, as a Study Hall member, you get to join my members-only tutoring support group. And I say support because we kind of need a lot of support in this class. And you can pose daily questions. So anything you have questions on with regards to organic chemistry, just post them every day. You'll get my help and help from my TAs so that you're never stuck, you're never alone, and that you have what you need to get through the course. The link again, leiaforsci.com/join. If you look at the molecule, if you look at the model kit here, then the idea of happiness, and I'll just leave this link up. The idea of happiness is molecules or substituents, they don't want to have anyone in their personal space. You ever talk to someone and they just come right up to you like that, and they're in your face and you're thinking, okay, I get that you're trying to talk to me, but take a step back. I don't need to smell what you had for lunch. And so imagine the molecule the same way. This right here and this right here, they need their own personal space, their own van der Waals radius of don't come so close, because if they do, they're actually going to push each other out of the way. So when you're talking to someone and they're too close, you might not want to push them away. These things will. And what will happen is the molecule will stretch and stretch and stretch and cause strain in the ring when they're stretching away. So the idea of happy, they don't want to be in each other's personal space. You do a ring flip, and now there's no issue. Look how these two used to be in each other's personal space, and now they're so far apart. There's nothing next to them. If you learned your Newman projections, you know that there are some Gauss interactions when you have them in this kind of conformation. So you still have some interaction here, but it's not as bad as this right here. So hopefully that answers your question. Equatorial, very stable compared to axial in each other's personal space. That's no good. Imagine, so when I started this session, my son was singing in his crib, and I'm pretty sure I hear him singing some more. There's a lot of wheels on the bus and Old MacDonald getting merged, so it becomes the chickens on the bus and the dogs on the bus, and we basically have a lot of that before he goes to sleep. But I think there's a lot less chickens right now and a lot more fussing. Don't worry, my husband's taking care of him, so that's why I'm not worried. Okay, look at this molecule right here. This right here, it seems to be fine because look, it's out of the way. But remember, these molecules can rotate, and it does not have free rotation. This thing wants to have free rotation, and it can't. So the bigger the molecule, the more substituents it has, the longer it is, the more unstable. You can see that it's kind of crashing in. But if I now take this thing and I do a ring flip, now look at this thing. It's free to rotate to its heart content. There's nothing in its way. I can turn this however it wants to go. And it's so stable because there's nothing to interfere. It's got all the space in the world. And of course, leiaforsci.com/orgolive, the pinned comment to get a copy of tonight's notes, the practice quiz, and so much more.